All right, let's start.
Hello, everyone. Welcome to another session of Book Club. So we were covering the third chapter. We've been discussing about the third chapter for the last couple of weeks. So we briefly covered B trees last week, specifically like how it is advantageous by using the 4KB pages and like having it in sorted order. So I was thinking we could go into like comparing B trees to Lsm trees, discuss about pros and cons. So if anyone has anything else that they wanted to add on B trees before we proceed further, we could take that. Else I'll just go. We'll just move to the comparison of B trees to Lsm trees. Okay, so so Lsm trees pros are like sometimes they have lower write amplification. So I think author discussed very nicely about what write amplification is. So I'll just read through what he has mentioned through this. Okay, so before that, what author says is like Lsm trees are typically faster for writes, whereas B trees are faster for reads. So reads are typically slower on Lsm trees because they have several data structure checks and SS table checks at different stages for compaction, right? So that makes sense because in case of Lsm trees, every time you want to read, you have to read it in the in-store memory index, and then again you have to go and check in all the segments like until you find it, right, from the latest to the oldest. But writes are pretty fast because you don't care about like finding the exact key to update it and all. You just append to it, and compaction happens at the back end. So so okay, so in when he talked about write amplification, what he talks about is like log structured indexes also write multiple times. So I think in case of Lsm trees, there are multiple writes that happen at the same time, right? Like we have indexes that needs to be updated, and we have segments that needs to be updated, and the compaction which is happening on the back end, which is a write operation. So in Lsms, we have like a lot of this write amplifications that are happening. But that's not the case with B trees. So that's one advantage that he talked about. And Lsm trees can be compressed better. So I didn't quite follow this because I thought like this is the same case with B trees as well, right? Because in B trees, we are not even having the duplicates and all. So I didn't quite follow this, what he meant by compressed better. The only advantage I found, I don't know if it falls into compressed. I thought it's more into segmenting because B trees write in 4K segments. You don't have like a proper segmenting, right? You always have this 4K segments that you used to write. Whereas for Lsm, that's not the case. I feel that's a segmenting advantage. I didn't quite follow the compressed better thing. If anyone has an advantage, understood it, probably you can explain.
Yeah, I can add to that. So the reason why this this point was mentioned is because in case of Lsm trees, it's like a hash map, so key and a value. But in case of B trees, what happens is a fixed block size is allocated, and the data is filled. So 4K, right? So 4K block is allocated. So on a disk, based on the sector, based on what block number it is, that entire block is allocated to a page. Okay. So until unless the entire data is filled, the other part remains empty, the unused part. So that's why he mentioned that compression is better in LSM trees and not in case of B trees. I hope that was clear.
Okay. No, I thought that is fragmentation thing, right? So fragmentation is better.
But yeah, even the space, right? Compression is not completely used, right? It's still some part of the data, some part of the allocation is unused.
Oh, okay. 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 So that I kind of got it. Like I thought that fragmentation, I thought compression is somewhere like the way it is stored in the disk, it is kind of a zipped or compressed and stored. That's what I thought was compression.
Yeah, that's the other one. Like, remember when we have the parse key, we have the key already sorted, right? So we have the, we keep the two key, and whatever between the two key can be compressed. Okay,
Oh,
so that can save that what he mentioned can save a lot of disk space and IO. And then if we go in, we search for that, and we can uncompress only that part and search for the value.
mm-hmm. So compression of the keys in LSM trees.
No compression of the data, right? So think about, we have the when we talk about the parse key, we have the key from handiwork and handy bag, and whatever between those, it can be compressed, right? Because instead of keep everything in between on disk, we can compress it to make it smaller.
Oh, but that's for B trees, right?
No, that's for the Lsm tree.
Yes, that's for LSM trees as well. Yeah, the author had mentioned this point somewhere. In case of sparse matrix, sparse indexes, what they do is they know the range data, they compress all the values and keep it. I missed this point. Yep.
Yes. Sparse indexes.
Yeah.
Yep.
So that's how we can save a lot of space. Plus, on top of on the B tree, we always need to allocate 4K block, right?
Mm-hmm.
And then,
okay.
Yeah.
But even in case of B tree, I thought like we have like a key similar way, right? We have range of keys that is stored in the top level tree and then goes down below like that, right? So it's already kind of compressed in such a way. Even
but the data, the value is not compressed. The value, the value at the leaf level does not compress.
The value at the leaf level is not compressed. Okay. Yeah. So comparatively, probably it's better. Okay. So that makes sense. Thanks guys. So, and they have lower storage overhead, especially when using leveled compaction. Okay. I think as when they say lower storage overheads, anyway, LSM trees, I think because they have duplicates, I don't quite agree to it, but okay. I think depending on the compaction they use, that might be an advantage, right? Did anyone also felt like that? So they say like LSM trees has lower storage overhead. Since we have duplicates, I never thought that's an advantage. Okay. So right amplification, I think we spoke about right amplification, right? Right amplification due to repeated compaction and merging of SS trees. Okay. So cons of LSM trees, the compaction process sometimes interfere with the performance of ongoing reads and writes. I think he talked clearly about like how many writes can be, the disk have their own capacity on how many writes that they want to allow. So depending on how many compactions that are happening, so that's an overhead. Uh, so the bigger database gets more disk bandwidth is required for compaction. If write throughput is higher, the compaction is not configured carefully. It can happen that the compaction cannot keep up with the rate of incoming. So yeah, he talked about things like how not, I think mostly these disadvantages are because of background compaction and background writes that are happening, and how that interferes with either reads, or how that interferes with if they are not compacted properly, how it impacts the uh, how it impacts the performance to find a key, right? If it is not compacted properly, it's definitely not going to be good index, good for finding the index. Uh, but at the same time, they also have to maintain the number of writes they can do on the disk, having lower priority for compaction versus actual writes. Okay.
Naga, I had one question.
Mhm.
So this is good. Like whatever we discussed was a hard with the rotating magnetic disk, but nowadays with the coming of SSDs, in which rather than updating the block, they also do the same thing. They create an entire new block and write it there. Does anyone have any idea like how does that work with the LSM trees, or I mean, or any other data structure like even a B tree and all? Like, do they work still well with the SSDs, or they still have a same interface that the disk has, or what it is?
I think he talked about it in a couple of places. So the what I found is like in case of disk, it's like you have to wait for the seek to happen to write to that location, right? But otherwise, like the number of writes that are needed and the number of writes that are uh, possible, I think still there is a bottleneck there. Like it cannot allow, the number of writes that it can allow are not like unlimited, both in case of SSD. In case of disk, it's like depending on the rotation speed and all, it has to wait for them, though the rotation speeds are pretty fast, it has to wait for them. So the blocks, both of them is the same. The number of writes and the wait time to write are again, I think in SSDs there's nothing like wait time to write because there are no seek waits. And in case of writes on SSDs, it's a disadvantage because when you look at LSMs, the disadvantage on SSDs are like there are only limited number of writes that can happen on SSDs, and after that, that SSD becomes unusable. So the more number of writes that you have, then the less usable the SSD becomes. So these are, I think, for everything that we are discussing, both in case of LSMs and B trees, we have these things come into play, especially write amplification comes into play for writes. And yeah, those are the things that I found. For blocks, if you're asking about writing blocks, I think both of them have the same process, writing the block of memory, right? Both of them have the same thing.
Yeah, earlier, I think earlier it was when they put the same interface in front of the SSDs. I mean, the same SATA 1, SATA 2, and SATA 3.
Mhm.
But with the new thing, PCIe, I think it's changed the way it writes to. I mean, I also don't have much idea, but I just heard like rather than inside the disk, right? We go at the location, we write it there. But here they do not write it. They just copy the block and create a new location for it, and then do a garbage collection on the old block of the data because they don't care about uh, updating in place.
Mhm.
But I may be wrong.
Yeah, yeah. Even if that is the case, the only advantage is like its writes are much faster, right? So earlier, if it have to wait for the seek to happen, when I say seek, it's like the rotation to happen before you can write, right? It's like uh, the rotation have to happen, and you have to wait for that memory to be available for the writer to write to the disk, right? In case of HDDs. So the it becomes faster. Like if it is not like really waiting, but it just stores it and then does the garbage collection later, it becomes faster, I think. Yeah. Anybody has anything else to add on that? Yeah, I had this question always, like whenever he talks about seeks and rotations and all, I somehow feel like there are no more HDDs that are being used in
Yeah.
data centers. So I don't know. That's something that if anybody is very familiar with like how most of this the cloud storages are set up, they're still using HDDs or like they're all SSDs now. Any other thoughts on that?
In the book, we
Sure.
mentioned that for the even for SSDs, uh, for random writes, SSD uses a LSM based technique to convert random writes to sequential writes.
Random writes to sequential writes.
Yeah, he
In case of LSM.
mentioned that in the same advantages and disadvantages. They use
The book? Okay.
similar. Yeah, I mean in the third chapter itself.
Mm-hmm. In the advantages of LSM. So I'll go over the notes that I have as well.
Yeah, on many SSDs, firmware internally uses a long structured algorithm to turn random writes into sequential writes on the underlying storage chips. So the impact of storage engine's write pattern is less pronounced.
Okay. So, I mean, Uday, are you saying like this becomes an advantage? So because we were kind of discussing on like SSD versus HDDs, all these advantages and disadvantages. How does that come into play? Are you saying like making that sequential doesn't matter what's the underlying kind of storage?
Yeah, no. I was actually trying to say, I mean, the amplification has a different aspect, but I was just saying LSMs are also used in the firmware for SSDs. I'm not saying about the impact of writes and these all random writes.
Oh, okay. Cool. Okay. Yep, that makes sense. Okay.
He actually mentioned a paper coding for SSDs or something in the index. I mean, if someone has read, we might, they can.
Coding.
I mean, we might have better explanation.
Which one, Uday? Coding
Coding for SSDs.
Coding for SSDs.
Yeah.
I don't know. In this chapter, I have read through indexing, other indexings and all. So I don't know if it is mentioned later, but I haven't read that part. Okay. So if no one else got that, let's jump to the next pieces. Okay, cool. So, so we were doing, we're talking about write amplification is done. Bigger the database gets, the more bandwidth the disk requires for compaction. Yep, we talked about compaction. The write throughput is high. Compaction happens. Compaction cannot be keep up with the rate of incoming writes. Okay, so I think this is mostly because of the compaction. Most of the cons are because of the compaction, I think. So I have some notes highlighted from my readings. if anybody has anything else to share on these things, please feel free to share those things. I can also read through some notes that I highlighted with my readings, and we can discuss those.
One thing I want to add is for the Lsm tree, they use only one thread, but B tree, it could be multi-threading. That means I'm talking about writing thread. So for B3, it would be multiple update, at the same time. So that's why in B3 they use the lock, to lock certain part of the tree. So not so it can avoid collision.
Yeah, that's right. That's an important point, right? Because it could be multi-threaded because it has like multiple indexes. But in case of LSM, it's always append only, so it has to be one thread for writing. Yep, that's right. Okay.
So for B trees also, like if multiple threads are writing, then it could create a problem, right?
But you are writing to like different indexes, right?
But what different index? Like there is one B tree, and if you like after the write, you don't know what might happen. You might have to split a node. You might have to do anything. And if the other write is also on the same node of the tree, then those like a write could modify the structure of the tree. And if other write is assuming the older structure, then the older and newer write might make
Isn't it where like I'm trying to think of it as a like that locking mechanism and isolation levels like we have in relational databases. We don't want all this, if there are concurrent operations happening, right? Like B tree, I'm thinking of like I have a B tree, which is more like again I'm talking in relational concept. So if I have a table and it's a B tree stored in a B tree structure, now when I try to, multiple transactions are trying to access a row or that table, I think we acquire different types of blocks, right? So that
you mean like one side of, but we wouldn't like I think is that Abhishek, like Abhishek was saying, what he's saying is like if it is a simple write, probably that's okay, you get a lock on that thing and then you write. But if the key needed a split, and that needs
that's what I'm saying, right? Even if like whatever kind of write, usually in relational, whenever you're trying to have a mix of reads and writes, like one transaction is writing, one is reading, or there are two writes happening, like concurrent. Writes can lead to anything, right? It can lead to a split. It can be an in place, just modifying the value. But there are so many issues that can happen, right? Even if I update in place, I don't split a node or anything. Update a value, right? I write something. Now, if I'm not enforcing proper isolation matrix, right? Like is locking, then other user can see. I mean, I think we'll talk about it in future, but in databases, there is this concept of, dirty reads and repeatable reads, right? So if one user is seeing certain value at a certain time, and then I try to read the same value again, right? I shouldn't, I mean, there are protocols which define what value I should get. I shouldn't get some, value that's not committed, or, I can roll back the transaction. All those concepts come in, but at a high level, the point where we are in a discussion, I don't want to, jump too ahead, but I think my short answer to that is there is this concept of lockings and isolation levels that are implemented.
Yeah, so let's think in terms of data structure, right? We have the B tree, the tree, and then lock, or you know what he called in the book he called latches. Latches, he said that lightweight lock. So you know, let's say we have we have multiple branches. So most of the time, the write, multi-write, each write will write to different branches. So that will be no problem, right? Then suppose that, two threads write, want to write to the same branch. Then because we lock it, only one thread can be, go through the critical session. And when it's done, the other thread can, can do it. So that kind of no, collision there.
Yeah, but even actually, Leon, on your point, even if there is a write that is going to two different, let's say, rows, right? We can't ensure that we can't say that we'll just let it go like that without any collision, even if there is no collision, but there can be chances of inconsistency. As a very simple example, there are two users logging in, right? Like trying to connect to a table, write to a table to two different rows, right? As a user, I don't know there is another transaction happening. So I go and write and update certain row with certain value from 1 to 2. And to me, all other rows are same. Now another user comes in and he or she updates another row from 3 to 4, right? And if you just, I think there are additional mechanisms that needs to be brought in, because otherwise to each of these users, two users, I'll get some data which I wasn't expecting. It's like, where did I just change from 1 to 2? How did 3 to 4 happen, or something like that? I think there are additional mechanisms to, kind of handle these kinds of situations. But yeah, I think.
Yeah, that is expected, right? Because one the first user complete the write and she got what she want, right? Then the second, because and the second user go and override it, that will be different transaction.
Right.
That's not collision there.
Yeah, but to Leon's point,
I think, yeah. Okay.
so what Leon is saying, like we can have this locks at a branch level. Is that what you're?
Yeah. But the branch is small level, so only lock what really needed.
No, Leon, but the problem could be, let's say your data was in different branches, but like as a result of your write, your parent node has to be updated, and both of them have the same parent, let's say. Then because of one write on a different branch, you have modified the parent, and that could create a problem.
Yes, then you have to lock at the parent, right? At
So
lock as small as possible.
Yeah, but then all of them have like eventually one parent, right? So you don't know up till what time, like you might need to then break his parent also, because that become full. Like I think in B trees, like the splitting can go up till all at the topmost level. So you don't know before the write where the splitting will stop.
Okay, so normally when you have you need to write something, right? You update one branch at a time, right? Let's say suppose you need to update two branches, and you say, okay, lock both branches, right? So nobody can write to that branch.
But when would you know that how many branches you need to lock?
Yeah,
because that part of you, like for example, you when you traverse from the root down, whether you update the data or you write, the new data, you can know, what node you need to go through, right? Just like binary search, you need to know what, node you need to go through, and that kind of branch, I'm talking about.
Yeah, but like in binary search tree, like to rebalance it, you might have to go up till the root node to actually rebalance, right? There could be situations that you have to change the root node itself to rebalance, and you don't know it beforehand that what will happen. So, and for every write, there is a possibility that you might have to modify all the way till root. So for the second write which has come, it had assumed that the root was the before root, but actually this write has modified the root, so you will create inconsistent data because the structure of the tree would have changed because after the result of the first write.
Yeah, last time we see about the B tree, right? B tree is bushy, right? That means that the chance of getting the root get updated is low, right? Because we have
You can't
many
say that it's
branches.
low. That's why I won't take a lock. Like, what if it happens? Like, what if it has very low chances also, but it happens? Then you have data in inconsistent state, right?
No, in that case, you need to know ahead and you lock the root.
But you
right?
know what I think. Sorry, Lian, go ahead.
Okay, go ahead.
I was saying like even it doesn't matter, right? Even if the node that we have to, I mean, the parent node splits up because let's say there is a node which two threads have to update, and then they would have already traversed by that time, right? Either both come at the same time, they already have a pointer to that node. So even if the root splits or what, they wouldn't matter much because they have already acquired the pointer to that point, and now they are just waiting for the one lock to release and then the other guy to acquire the lock.
So I think we have I just pulled up some example here. So if the where we will rebalance the tree is, let's assume like this tree is talking about like from 4 to 32 we have it here, and 32 to 64 we have it here, and above 64 we have it here, right? And that goes down. And now we could get to a point where we want to split this 64, like because 64 is covering like 64 and above and all, right? So we might want to split this up and get one more added here, which is like 64 to 90 or so.
Right, but this one only have 3 nodes, right? With B3, we have many branches, so the chance of splitting a node is low.
Yeah, low, but how would we know when that is low? You don't know until you go try to add it, and you realize that, oh no, I need to add something or update this root node. So when you update this one,
well,
in some cases you update only this node, but in some cases you will have to update this node.
Okay, so let's think, the branch factor, right? Let's say when you traverse from the root, if the root is, still have a lot of empty spaces, then that you don't need to lock it there, right?
Right.
Only when the branch is when it already full, then we have to split it.
Mm-hmm. Right. Yeah. Only when there is there's no space that you want to split it.
So that's why I think B3 make it very bushy in that case. It make it less chance to split the parent.
Yeah, that's definitely advantage. But is that deterministic always is what I think we were discussing, right? Yeah.
And I think in the databases, they guarantee that only one writer gets the lock is at the row level. Means I think at the one node inside that whole set of nodes at that particular point.
Only here, one lock on this node is what we're talking about.
I think they say at row level, at each number, I would say, like numbers, like number 89 or index. 92. Mm-hmm. Yeah. So,
yeah. But I think that's where, right? If you only lock it here, if something gets updated here because of some change in here, then somebody could try to add it here, which goes here instead of, yeah. I think it's could be maintained. Probably that will be discussed further on, like how it can be done. But definitely in case of B trees, that's an advantage over LSMs where it's only append only, right? In case of append only, then you don't have a choice, but you have to wait for that to be completed before you can do another write. Okay, that's good. So okay, so let me quickly. Do you guys want to start the indexes, other index structures, or let's go through some of my notes, or because we have 5 minutes and we wanted to discuss on like how we want to look at the voting and take forward. Okay, so let's do this for 5 minutes. I have some notes that I have highlighted when reading, so we can read through that. If there is anything interesting, we can talk about it, or we can look at the poll that we created and how we want to do this session in the coming weeks. The advantage of B-tree is that each key exists exactly in one place in index, whereas log structured engine, we have multiple copies. I think that's definitely a true advantage, right? And other point I had on downsides of LSM is compaction. We talked about it. Lower amplification, we talked about it. Same page twice to avoid ending up partial updates. Yep, I think those are the points I had in my notes. Okay, so I mean, we could go to the next topic is all the other indexing structures. So I think where he talked about clustered index and multi-column indexes, full text indexes, and other stuff. I think let's cover this in the next session and try to finalize on how we want to do this session going forward. There are a couple of interesting ideas that were discussed in the Discord. I think we have been postponing this, and so let's spend some time to get that thing.
Should I stop the recording?
Yeah. So